The James Webb Space Telescope just pointed its mirrors at the aftermath of two galaxies violently colliding, and what it found inside that cosmic wreckage has forced astronomers to completely rethink what happens to star formation when galaxies destroy each other. Galaxy collisions are among the most violent events in the observable universe, and they are far more common than the word collision implies. When two galaxies merge, they do not crash the way cars crash. The distances between individual stars are so vast that direct stellar collisions are extraordinarily rare during a galactic merger. What collides is the gas, the dust, the dark matter halos, and the gravitational architecture of two entire island universes, each containing hundreds of billions of stars, interpenetrating each other over timescales of hundreds of millions of years. The result reshapes both galaxies permanently and triggers processes that determine the fate of star formation across the merged system for billions of years afterward. Webb recently turned its instruments toward one of the most studied galactic collision sites accessible from Earth, the Stephan's Quintet, a compact group of galaxies in the constellation Pegasus, approximately 290 million light-years away. 4 of the 5 galaxies in this group are engaged in an ongoing gravitational interaction and merger sequence that has been observed for decades. But what Webb's near-infrared camera and mid-infrared instrument revealed inside this collision zone went significantly beyond what previous telescopes had been able to resolve. Webb detected massive shock waves propagating through the intergalactic medium, the diffuse gas that exists between galaxies, at a scale and detail never previously imaged. One galaxy, NGC 7318b, is plowing through the group at approximately 800 kilometers per second, driving a shock wave larger than the entire Milky Way through the surrounding gas. Webb's spectroscopic instruments measured the temperature, density, and molecular composition of gas being heated and compressed by this shock to temperatures of millions of degrees, conditions that simultaneously destroy existing molecular clouds where stars form while potentially triggering new star formation in compressed regions along the shock front. The tension Webb revealed inside this collision is scientifically extraordinary. Galaxy mergers have long been understood to trigger starbursts, episodes of dramatically accelerated star formation driven by gas compression. But Webb's data from Stephan's Quintet shows that the same collision process simultaneously suppresses star formation in other regions by heating gas to temperatures where it cannot cool and collapse into new stars. The merger is both creating and destroying the conditions for stellar birth across different regions of the same system simultaneously, a duality that previous instruments lacked the resolution and sensitivity to map in this detail. Webb also detected molecular hydrogen emission across vast regions of the collision zone, glowing gas tracing the shock interface in infrared wavelengths completely invisible to Hubble. This molecular hydrogen represents gas caught between being heated to plasma temperatures by the shock and being cooled by radiative processes, existing in a transitional state that determines whether it will eventually form stars or disperse permanently into the intergalactic medium. The ability to map this transitional gas at the resolution Webb provides is entirely new to astronomy. The black hole activity Webb found embedded in this collision adds another layer of complexity. The galaxy NGC 7319, at the center of Stephan's Quintet, hosts an active galactic nucleus, a supermassive black hole actively consuming surrounding material and releasing enormous amounts of energy into the surrounding gas. Webb's spectroscopy revealed that this black hole's energy output is interacting with the collision shock waves, creating feedback loops between the merging galaxies' dynamics and the central black hole's activity that influence star formation rates across the entire system. What makes Webb's observations of galactic collision sites uniquely valuable is the combination of spatial resolution and spectroscopic capability it brings simultaneously. Previous infrared observatories like Spitzer could detect the heat signatures of collision activity, but lacked the resolution to map where specific processes were occurring at subgalactic scales. Hubble had the resolution, but was limited to visible and ultraviolet wavelengths that cannot penetrate the dust clouds dominating the most active collision regions. Webb sees through the dust in infrared while resolving features at scales comparable to individual star-forming regions, a combination that has simply never existed before in astronomy. The Milky Way itself is on a collision course with the Andromeda galaxy. The two largest members of our local group of galaxies are approaching each other at approximately 110 kilometers per second and are predicted to begin merging in approximately 4.5 billion years. What Webb is revealing about the internal dynamics of Stephan's quintet is therefore not purely academic. It is observational data about a process our own galaxy will eventually undergo, playing out in a system close enough for Webb to study in extraordinary detail. Every galaxy collision Webb examines is adding data points to a model of how galaxies evolve, how star formation histories are shaped by mergers, and how the large-scale structure of the universe, the cosmic web of galaxy filaments and clusters, was assembled through billions of years of gravitational interactions, exactly like the one Webb is currently mapping in Stephan's quintet. The wreckage of two colliding galaxies is not just destruction. It is the universe's most dramatic mechanism for building the next generation of stars, planetary systems, and potentially the conditions for life, written across hundreds of millions of light-years of cosmic real estate that Webb is now reading with unprecedented clarity. So here is the question that should genuinely shift how you think about cosmic scale. If the Milky Way and Andromeda colliding in 4.5 billion years will trigger the same shockwaves, star formation bursts, and black hole activity that Webb is mapping in Stephan's quintet right now, and Earth will likely survive that merger as a planet, what kind of night sky would a civilization on Earth see during the billions of years that merger takes to complete? Follow this page right now if Webb's discoveries make the universe feel genuinely alive to you, because we break down every major observation with the depth and clarity it deserves, every single week.